Hi, my name is Jennifer Vang. I am an electrical engineering graduate student here at University of Michigan Dearborn. My presentation today will be on adaptive cruise control systems, which is also known as ACC systems. I will begin by covering what an ACC system is. I've also included a list of vehicles with ACC systems. I thought this would be fun to review. We will also cover the overall system dynamic. Then I'll dive into a study conducted that helped support the improvement of ACC systems. We will then get to look at a MATLAB simulation of an ACC system using model predictive control. Finally, I will conclude this presentation with where ACC systems are today. So what is ACC? ACC is adaptive cruise control, and it's a driving system that maintains a set speed based on users' input. The main purpose is to create a safer driving experience for the user and other drivers on the road. As previously mentioned, the systems maintain a set speed, but more importantly, it will decelerate the vehicle when obstructions in the vehicle surrounding areas are identified. Most of the time, the ACC system user input to maintain a desired speed is on the right side of the steering wheel, as shown in the image on the right. Here's a list of vehicles with ACC systems. I drive a 2019 Toyota RAV4 and take many trips to Chicago or Toronto. I utilize this feature a majority of the time and I love it. I also tried to include a list of each OEM to display how many different companies across the world implement this feature. And as you can see, it's a pretty diverse list. From most of my research, most vehicles from 2018 and up usually have this feature. In addition, a poll was conducted last November that provided a list of the new vehicles with the best ACC system. So, for example, the 2022 Mazda 3 utilizes a radar to scan the distance between itself and the lead driver, which displays to the user what the actual distance is. And then the 2022 Honda Accord offers the ability to set two distances, one for the vehicle in front of the driver and then one for the vehicle behind the driver. ACC systems that are used in vehicles today are mostly linear. Autopilot and airplanes would be an example of a nonlinear system due to more unpredictable factors such as consideration of complex trajectories. Therefore, the X, Y, and Z axes are required when developing this type of control system. Before digging into the controller components, let me provide some ACC vocab that'll help you better understand the terminology as I speak throughout my presentation. The ego vehicle is the car being studied, or the car in subject, sometimes referred to as the host vehicle. The leader vehicle is the car in front, sometimes referred to as the preceding vehicle. And then the following vehicle is the car behind the leader vehicle, if speaking in third person, or behind the ego vehicle, if speaking in first person. The ACC system consists of two controller components, an upper level controller and a lower level controller. The upper level controller calculates the desired acceleration that's inputted in by the user. There are different approaches, such as the model predictive control algorithm, a PD controller, or like a PID controller that can be used to calculate this. However, in this presentation, we will mainly be focusing on the model predictive control algorithm. Now for the lower level controller, that calculates the actuator input, which is the throttle angle or the engine torque that's required to track the desired inputted acceleration provided by the upper level controller. In the upper level controller block, as you can see in this flow diagram, sensors such as radar can be used to detect the distance and speed of the leader vehicle. This data is then collected in Fusion or pre-processed. Then algorithms are developed to compare the performance between the algorithm itself and what's been collected by the sensor, which allows the overall system to make a decision on whether or not it needs to accelerate or decelerate. In the lower level controller block, the first half focuses on the throttle. The throttle angle will be calculated to help support locking the desired acceleration received from the upper level. This information is then fed into the engine to output the correct torque value. The second half of the lower level controller block focuses on the powertrain dynamic model. This is basically a one-dimensional mechanical system as shown in the image below. Here, the engine torque value is received and calculates the appropriate traction force that's required to maintain the desired distance dependent on the car's velocity. In 2014, a study was conducted to identify human driving habits in order to develop an algorithm using MPC, or Model Predictive Control, that mimics human behavior. For starters, MPC is a feedback algorithm that uses a model to make predictions about future outputs of a process. So, for example, the goal is to make the best predicted trajectory as close as possible to the desired trajectory. Now, in many cases, MPC is often used because it can handle multiple input, multiple output systems that may affect their inputs and outputs. But that said, a huge advantage to MPC is that it's a multivariable controller that controls the outputs simultaneously by taking into account all the interactions between system variables. When developing the MPC algorithm, the authors began by identifying the desired distance between the lead vehicle and the ego vehicle. The spacing error and relative velocity are then defined to act as a reference for the feedback controller. State vectors are assigned as shown in note number 3, and then the acceleration of the lead vehicle is identified as the disturbance. In the first simulation scenario, the ego vehicle follows the lead vehicle at various speeds. This resulted in a large space between both the vehicles, concluding that there is a potential lower risk of collision occurring. In the second scenario, the ego vehicle approaches the vehicle moving at a constant speed. This resulted in a various acceleration pattern and deceleration occurring more often. Now, with that said, this could result in a potential reaction time being delayed. In the third scenario, the ego vehicle is cut off by another vehicle, which surprisingly resulted in a smoother sudden movement when using MPC algorithm. This smooth result can increase the comfort of driving experience for the user and also increase the reaction time. In the fourth scenario, the ego vehicle is following a lead vehicle that changes lane. Now, as a result, when using the MPC algorithm, the ride was also much smoother here. Moving along, the following MATLAB simulation uses MPC algorithm to display how ACC systems work. Similar to the case study, a sensor is used to measure the distance and relative velocity of the lead vehicle. The overall system operates in two modes. The first mode is speed control, which allows the vehicle to travel at a desired speed. Now, this mode is enabled to track the driver's set velocity. The second mode is spacing control, which allows the vehicle to travel at a safe distance. This mode is enabled to maintain a safe distance from the lead vehicle. As shown in this diagram, the left block includes information of the lead vehicle where the acceleration, initial position, and initial velocity are collected as an input. This information is then passed through to the sensor to read and collect the initial position and initial velocity of the ego vehicle, which helps feed the acceleration of the ego vehicle as the system's output. In this example for Simulink, the initial position for the lead vehicle was set to 50 meters and its initial velocity was set to 25 meters per second. For the Eagle vehicle, the initial position was set to 10 meters and its initial velocity was set to 20 meters per second. And then the desired velocity was set to 30 meters per second. Looking at the plot with those given inputs, the first 3 seconds in the lower plot show that in order for the system to reach the desired set velocity of 30 meters per second, the Eagle vehicle had to accelerate at higher throttle. Then you'll see between 3 seconds and 13 seconds, the lead vehicle begins to accelerate slowly, resulting in the Eagle vehicle needing to accelerate at a slower rate in order to maintain a safe distance. Now, as shown in the middle, between 13 to 25 seconds, the Eagle vehicle's velocity will remain at 30 meters per second. And then between 25 and 45 seconds, it is shown that as the lead vehicle decelerates and accelerates again, the Eagle vehicle follows the same pattern while simultaneously maintaining a safe distance. In closing, ACC systems help keep all drivers on the road safer. As previously mentioned, most vehicles that are of the year 2018 and beyond usually already have this system feature provided in the most basic vehicle edition. As of currently, the automotive industry is racing towards the world of autonomy, right? So as we continue to move towards this world of autonomy, not only does the progression of ACC systems help feed into making autonomous vehicles more reliable, but this data in the human behavior study that was previously mentioned can also support the idea of having both autonomous and real drivers on the road at the same time. Overall, this can help improve systems such as vehicle to vehicle communication if society ever came down to that point. Now, with that said, most of ACC's studies today look into human behavior and psychology to better provide a more accurate, efficient, and safer driving experience for all vehicles on the road by mimicking the real life human behavior traits. Thank you.